I'm Kate.
And our project is implementing parallel processing on a Raspberry Pi Beowulf cluster.
So, my name is Kate, and this is my second 3SP summer. Basically, last summer we laid the foundation for this project. We got the show started, and the team was me, Abe, Hannah, and of course our beautiful technology guru Sadiq. So what we did last summer was basically how it all began. It began when Louis and Professor Sivo had this great idea of setting up a data center especially for the STEM projects. And so we began to research how it would be implemented, what's the most budget-friendly way to implement a great data center that would be powerful but also not too costly, obviously. And what we started to do is we started researching the Beowulf cluster. And basically, it's the technology where you take commodity-grade computers or mini computers like we did. We took Raspberry Pis, you connect them together through a LAN, you implement message passing interface software on it, and it allows you to process your software, process your code parallelly on all the nodes. So this is what we did. This was our cluster last year. There was only 4 Raspberry Pis connected to a LAN switch. This was the master node, and it was sending out the directions to all the other nodes to basically parallelize the code and to get better performance out of it. So you can see it on the screen here that you basically can't see it, but yeah. So this is all the 4 nodes running one and the same program at the same time. And as you can see, it decreased the time of processing greatly. So we were running testing software on it, I think we were using some calculus, like we did area under the curve of x squared, and we ran it on 4 Raspberry Pis. As you can see, moving from 1 core, each Raspberry Pi have 4 cores. So moving from 1 core to 16 cores, the time decreased greatly, so it proves the efficiency of the system. That was our results, and this was the poster presented at the Stanza Square, where this project won 2nd place. And it was the only IT computer science project awarded. What is the difference between a supercomputer and the cluster? Basically, there is a very little difference between a supercomputer and the cluster. Not all clusters are supercomputers. Like, for example, this 33-node Beowulf Raspberry Pi cluster probably isn't a supercomputer by modern standards, but most of modern supercomputers are clusters. And today I am very happy to present you IBM Summit Supercomputer. Basically, this is great news because only just recently, it only happened like a couple of weeks ago, this computer was implemented at Oak Ridge, Tennessee National Lab Research, and it was sponsored by Department of Energy, if I'm not mistaken. And US now got its first place in the supercomputing industry, which belonged previously to China. This was previously the best supercomputer, Sunway Taihu Lite, and it benchmarked 93 petaflops. This beauty benchmarked 200 petaflops. 200. Yeah, so it's more than twice the previous record. Okay, that concludes my speech.
Okay, so we achieved a lot of our goals in summer 1. We designed and assembled a case for the Beowulf cluster, as you can see here. As one can see in the top right corner, it is an image of the finished blueprint that we ultimately used for the design of our case. There have been numerous alterations to the blueprint, such as spacing, scaling, and changing in the dimensions. We started on the second goal in the beginning of the summer, which was to connect 15 standard school desktop computers to compare and benchmark the processing power of the two to see which one would compute faster. So I proposed and executed an idea that would minimize the cluttering of the wires and increase operating space before the wires would tangle with each other. So an easy fix was just to buy shorter Ethernet cables and micro USB wires. The image that you see was an assembly of a mock-up of the actual design. This was done to physically see if all the cables would reach. So previously, as Kate said, in the previous summer we had 4 Pis. However, this summer we increased it to 8 Pis. And to do this, I had to recommunicate the Pis again. And as you can see here, I created I wrote a script, dot/checkpings.sh, and basically that just checks the pings of all of them to make sure that everything is communicating, all the pies are communicating.
Okay, so to fit this all into an enclosure, we had to make sure the enclosure satisfied 3 conditions. It was portable, efficient, and presentable. To make it portable, as you can see here, we made it out of lightweight cast acrylic, so it's easy to just pick up and move around to any show floor. And to protect the pies, the cast acrylic would also protect it since it's a very sturdy material. To make it efficient, the small size of this provides a smaller distance for the data to transfer to each pie through the Ethernet cables. So it allows for faster processing time, even if it's by a few milliseconds. And for it to be presentable, the cast acrylic, as you can see, is see-through. So when we're presenting it on a show floor, people can see the components that are working inside of it. So we have nothing to hide. We also added some LED strips to catch the viewer's eye and to attract people to this computer. And also, additionally, this fan is very silent but efficient, so it can pass through air through the pies to cool it.
Okay, so this is a bird's eye view of our enclosure. Basically, we had a few components that were too. Okay, so we changed the USB hub because the previous one was a 13 port, and it did not have enough power to supply all these pies. So we increased it to a 10 port hub that's 60 watts. And the main power strip originally was too long, so it would not be able to fit into the case. So we just bought a 3 outlet surge protected power strip. And you see the fan, the holes for cable management. It's still a little compact because some of the wires are still in the way, but we can fix that.
So for those of you who can't see, this is a close-up of what's inside the enclosure. So as you can see, the pies are mounted onto a custom-made cast acrylic wall, which was laser printed. They're held together by, you can't really see here, but they're held together by spacers and screws, which are also screwed in. Here, we made 2 holes here and here on the bottom side of the pie walls to allow all the cables to pass through very efficiently and very organized. And as you can see, the fan's right here, so it blows through past these pies to the ventilation shaft, as demonstrated there, to again cool off the pies and improve efficiency.
And going forward, it's a little clustered right now, but we are going to order larger screws so we have more space, so we can kind of elevate the pie so the HDMI cable can fit. It can't fit right now because everything's too narrow, but I'm trying to like increase the elevation.
So how do we make a case like this? So first, to laser print all the details into the cast acrylic, and also to make the sheets of cast acrylic used to make that, we needed to use a software called AutoCAD, which is a software where you can just you can architect 3D images on it, and then you can use that to laser print whatever you want on a compatible laser printer. However, with the laser printer that's available at Bergen in the machine shop, it doesn't exactly take AutoCAD drawings. So what we did was we designed the designs in AutoCAD, as you can see here. So then we saved that AutoCAD file on the computer. Then we exported that file as a PDF file because the laser printer also accepts PDF files. We downloaded that onto a USB drive. We brought it to the machine shop, plugged it into the computer, and successfully printed out all the components of the supercomputer enclosure. So as you can see here, with the support of Mark Balzaret, he was able to align the laser cutter and teach us how to properly use it so we can cut it out. This is Connie and I filing down some corner brackets, so to be able to fit these pie walls in here, just to slide them down, and they're also easily accessible to pull up in case if anyone needs to access the pies. And this, as you can see, is the laser cutter actually cutting a piece of cast acrylic. It's a screw hole that we use to screw into it. And yeah, and this is Connie and I again applying some cast acrylic solvent onto the corners to form a strong bond to ensure that no outside debris can penetrate the case. We did encounter some problems along the way of building this case. One of the first problems that we encountered was the original dimensions provided to us were a little too small, so the wires here do get a little crowded, and it is a little difficult to pull this up to access the pies. So that's one problem we faced. As I said before, the AutoCAD drawings weren't exactly compatible with the laser printer, but we worked around that by exporting it as a PDF file. The laser cutter scale at first was very off at first because when we first tested our drawings on a piece of mat board, the original cutout of it was as big as my finger, so we couldn't really use that. But over time, we reprogrammed the laser cutter to cut out to a 1:1 scale, so we fixed that.
Okay, so as you can see, if you look closely, there's a lot of unneeded holes. That was because we had to change some designs a little bit, and we kept on changing the design to make it more efficient. And again, as you can see, there are cables. It's like all over the place, and there's not enough like space to put all the cables through.
So yeah, you can follow us at our blog for more information. We post daily, and if you would like to join us build this supercomputer, especially on our Phase 2 project, the information on how to join is on our blog, and anyone is welcome to join.